somewhere.
Oh, sure.
Just for your interest, Pradeep Garg from CPWD. Right now he's in Jaipur. He's also joining. As an attendee, of course. You may not see him.
We can start. Sir. Vinay sir, I think we can start.
Yes, certainly, Mr. Joshi.
Yeah. Deepika, please.
Good evening, everybody. I welcome you all to the Indian Institution of Bridge Engineers live webinar today. We will be having various topics on cable-supported bridge design. So, Mr. Mahesh Tandon, Professor Mahesh Tandon, and Dr. Boris Reyher will be presenting. So, I would now request Ruhi to please present the guidelines for our participants today. Hi, Rui. I request you to please present the guidelines for the participants today.
Just call her up on the phone to check.
I think, Deepika, you can continue. I suppose she is facing some technical problems. You can continue with the guidelines.
I think she's joined back. She'll start now.
It's unmuted. She's muted, I think.
Rui, you have to unmute yourself. We are not able to hear you.
Hello.
Yes, you're audible.
Yeah. Before we start the event, I would like to read basic rules and guidelines for all the participants. All participants will remain on the mute mode during the lectures. Questions should be put in the question answer slot. After the lectures by the speakers, question will be replied by the speakers panelists. Subsequently, attendees can raise hand from the option below at screen. During questions, specific participants will be unmuted by the organizers. After the participant's question gets over, the participant should mute himself. Participant's video will not be displayed on the screen. Speakers, panelists can share screen. Now, I would like to hand over to our host. Thank you.
Next, I'd like to introduce Engineer Swapnil Joshi, who is the Honorary Secretary of IIB. Swapnil Joshi is an intellect who possesses bachelor's in civil engineering and double post-graduation from United Kingdom and NICMAR with specialization in construction project management along with law graduation. He has wide exposure in developing systems, has developed expertise in the field of CPM, combining technical and latest management tools such as Primavera, Asta, Power Project, Tylos, etc. He initiated and developed a mobile application Nintendo projects for daily monitoring and real-time data analysis of projects. With successful implementation of digitalized integration approach and his expertise in project planning, BIM and advanced technologies, he is able to deliver the client goals successfully. Swapnil has been rewarded by Indian Institution of Bridge Engineers from the hands of Shri Nitin Gadkari, who is the Union Minister for Road Transport, Highways and Shipping in 2014. So I would request Engineer Swapnil Joshi to please come and host the event. Thank you.
Thank you, Deepika. I formally would like to welcome all of you for this special lecture series 3, where we will be having two amazing personalities delivering a special talk today. I would like to formally welcome our Director General, Engineer DG Divte, IIB President, Engineer Vinay Gupta, who will be the moderator for today's event. Today's eminent speakers, Professor Mahesh Tandon, Managing Director, Tandon Consultants Private Limited, Dr. Boris Reyher, Director, SBP Germany. Our panelists, Dr. Harshvardhan Subbarao, Chairman and MD, Consumer Consultancy Private Limited, Engineer V.N. Hegde, Chief Executive Officer, Stoop Consultants Private Limited, and our my colleague, Secretary, Dr. Gopal Rai. With this brief, I welcome you all for today's event. Let's go next, Ruhi. I would like to give a brief about IIB. Next slide. Okay, before I'll just start till it's yeah. So Indian Institution of Bridge Engineers was established in year 1989 by late Sri Engineer MC Bhide, Chief Engineer Indian Railways, with the aim to promote bridge engineering in the country. After sad demise of Sri MC Bhide on 7 July 2018, IIB strives to continue to promote bridge engineering with the same enthusiasm and passion. IIB is the only professional body exclusively dealing in bridge engineering. Spread over 33 states and local centers with about 7,000 strong member force and 169 institutional members, IIB has created laurel for the country. It has also published 29,200 pages of technical literature, and IIB holds outstanding Bridge National Awards competition for encouraging the good work done in the industry. With this brief introduction, now I would like to introduce our Director General, Engineer DG Divte, and I'll request him to take the forum once I introduce him and to say a few words about IIB. Engineer DG Divte graduated in civil engineering from College of Engineering Pune in 1974. Through 1975 UPSC exam, he joined Indian Railways Services for Engineering IRSE as Class 1 officer and retired as Principal Chief Engineer of Indian Railways in 2011. During his service, he worked on many important railway infrastructure projects. He occupied the important post of Principal Chief Engineer, Northeastern Railway and Southwest Railway, Director, Board Member of Konkan Railway Corporation, Chief Engineer Konkan Railway Project, Chief Project Manager for Tunnels of Mumbai-Pune Expressway, Project Director of Katra to Lole portion of Udhampur, Baramulla, J&K Railway Project. And recently he was on Mumbai Metro 3 to 33.5 kilometer long, fully underground metro construction project as CGM. With this brief introduction, may I now request our Director General, Engineer DG Divte, to say a few words about IIB. Over to you, sir.
Thank you, Swapnil. Hello. Hello.
Yes, sir. Go ahead. Yes,
thank you.
We can hear you.
Thank you, Swapnil.
Yeah.
All the
Thank
dignitaries, eminent panelists, respected speakers, delegates, and all the participating engineers in this special lecture series, Lecture-3, on the subject of overview on challenges in cable-stayed bridge designs and case study on cable-stayed bridges. I welcome you all for this special lecture. As Swapnil has briefed, this IIB, Indian Institution of Bridge Engineers, was established in the year 1989 by Engineer MC Bhide. He was railway engineer, retired as Chief Bridge Engineer of Indian Railways. He had vast experience of bridge design, construction and maintenance of bridges over the period of about 35 years. And during this period, he felt the need of special institution, another dedicated institution for bridge engineering, since bridge engineering is a vast subject. And in the existing Indian Institute of Engineers, the bridge engineering is dealt as a part of the civil engineering and it does not get this due attention or due representation. And that is why he felt the need of special institution and he started discussing this issue with various engineers, the topmost experienced engineers of government departments like Indian Railways, CPWD, PWD, MES, border road engineers, and then at the end he decided to lay the foundation for the institution. In 1989, finally this institution was formed and then it started functioning. During last more than 34 30 years, it has achieved many milestones. As Engineer Swapnil has briefed, we have number of chapters all over India, a number of more than 7,000 members and institutional members, and lot of activities have been carried out. I think I will not repeat all these details. The IIB has a mission of bridging the gaps in intercontinental and intracontinental, and building the bridges of camaraderies, understanding, friendship, and cooperation amongst engineers, not only in India, but of the world. And to collect and document all aspects of technology relevant to bridge engineering, and disseminate the same to entire engineering fraternity, right up to grassroots levels of engineers. So, and since this being the only dedicated institution for this railway engineering, it provides common platform amongst all the stakeholders to disseminate the technical and skilled knowledge, experience gained for speedy constructions and quality works, recent developments and innovations in the field of bridge engineering and related products. So during last 30 years, we had number of national and international seminars, roundtable workshops, the outstanding bridge awards to appreciate or to recognize the good work done by the engineers, designers, contractors, and owners. So such 10 functions were held, and the outstanding work was recognized by IIB. Now recently, when we completed 25 years, the IIB celebrated its Silver Jubilee function in Mumbai, which was graced by as chief guest by Sri Nitin Gadkari, Union Minister for National Highways, Roads and Shipping. After sad demise of Sri MC Bhide in August 2018, we have revived all the activities of IIB and continued all the activities with same zeal and enthusiasm. We started evening lecture series. We started conducting the seminars as we were doing earlier. The last year we had a seminar, our annual bridge function at Patna, and this year, because we could not hold the seminar because of this COVID situation, we had the webinar. In last 12th and 13th June, we had a very successful webinar, our annual function. And now we are conducting this lecture series also on webinar. Today's lecture is third lecture. Lecture is very interesting and very interesting to all of us. So I welcome all of you once again, and I wish all the success to today's special lecture series. Thank you all.
Thank you very much, sir, for a great introduction and the work done by IIB till now, and our updates on the webinars, successful webinars.
Swapnil, 1 minute.
Hello. Yeah.
I'll take 1 more minute.
Yeah,
hello.
Sure.
Today, Mr. B.P. Khare, retired General Manager of Indian Railways, is with us. He has joined from Bhopal, so I welcome him to this group. He was our old member of IIB, and now he has rejoined with us. Mr. Khare, after graduation in civil engineering, joined Indian Railway Service of Engineers through UPSC in 1977. 1976 batch, joined in 1977. Since then, he was in railway service, and during his service, he had executed number of infrastructure projects. He was in operations, he was in construction projects, he was in design area, and he worked as divisional railway manager, and he worked as general manager of Central Railway also. After retiring as general manager, he worked as a project director of general consultancy contract of Chennai Metro. Now he settled at Bhopal, and when I was talking to him, he was very happy, and he has immediately agreed to join IIB's activities and start the activities at Bhopal also. So I welcome him on with us. Thank you.
Thank you, Mr. Devte. Thank you.
Thank you, sir. Thank you very much. Now I'll introduce our president and today's moderator for the session. Engineer Vinay Gupta. Mr. Vinay Gupta is a civil engineer from BITS Pilani, 1983 batch, and director and CEO at Mrs. Tandon Consultants Private Limited. His specialization is in bridges, flyovers, underground and elevated metro structures, recast buildings, 275-meter tall chimney, etc. Active member of various code committee of BIS and IRC. His contributions include preparation of IRC SP65 segmental bridges, IRC SP71 recast pretension girder bridges, etc. Recipient of several awards from IEI, IBC, and UKIERI. He has been lecturing as guest faculty in IIHE, CRRI, CIDC, ISDA, DPC, etc. Engineer Gupta is the All India President of ICI, Indian Concrete Institute, as well as our institution, Indian Institution of Bridge Engineers. With this brief introduction, may I now request our President and today's moderator, Engineer Vinay Gupta, to conduct the further session, and along with the brief introduction of IIB, and then please take it forward. Over to you, sir.
Okay, thank you, Mr. Joshi. So, good evening, friends. I hope we have not disturbed your afternoon nap or something. It is always good to have Indian time coincide with the German time. So we requested Dr. Boris Reyher, and he would normally prefer a time which is their afternoon and our evening. That's where he is in Germany. Just a little bit about these two of this our back of the office people. You heard a lady called Deepika Singh. She happens to work in Intento Consultants. She's an engineer, and out of her deep interest in the field of bridge engineering, she has volunteered her some parts of the services to IIBE. Similarly, we have Messrs. Ruhi Agrawal from DGC, that's a company who deal with repairs and rehabilitation of bridges and buildings. And she's also volunteered some of her services for this good cause of dissemination of knowledge by IIBE. Now, today, in addition to whatever you must have been hearing, before that, Mr. Swapnil Joshi, he is the managing director of, who was speaking just now and welcoming everybody. He is the managing director of Intento. I think he was briefly introduced by Deepika Singh. Today, apart from whatever you have been hearing, that is the lecture or the case studies by Dr. Boris Reyher, we will also hear briefly, to warm up the whole session, Professor Mahesh Tandon to say a few words about what all cable supported bridges are and where all they exist, say in India or abroad. A little bit of a brief before we get to the serious session by Dr. Boris Reyher. A few words, and of course we have two panelists, Dr. Harshpradhan Rao and Mr. V.N. So first of all, a few words about the panelist, or about the first speaker, Professor Tandon, who will warm us up and bring our mind. been
Vanessa, I'd like you to please unmute your mic.
So when did I get muted?
So there was some network interruption from your end. I think now it's clear. We were unable to hear you in the middle.
Okay. When did I get?
Still, it's not
Okay.
clear.
Nobody seems to hear me. Anyway, I'll keep speaking. So Professor Mahesh Tandon, he is a managing director of Tandon Consultants Private Limited. He is also a guest professor at IIT Gandhinagar, and he's an international expert.
I think we have a network interruption from Mr. Vinay Gupta.
Deepika, you can just read out the introduction. So once Sir joins back, he can take it over.
Yes. Okay. I'd like to introduce Professor Mahesh Tandon. He is the speaker for today's session. He'll be speaking on overview of cable-supported bridges. Professor Mahesh Tandon is the Managing Director of Tandon Consultants Private Limited and guest professor IIT Gandhinagar. He's an international expert in the field of structural engineering. Many of these structures designed by Professor Tandon have been widely acclaimed and have received recognition in India as well as internationally. He is honorary fellow Indian Concrete Institute under the AICTE INAE program. He was appointed Distinguished Visiting Professor at IITs at Kanpur, Roorkee and Gandhinagar in 2005 to 2015. He has accreditation of International Professional Engineer India. Recently, he was given the Distinguished Alumnus Award by IIT Roorkee.
Well, I can tell you he has received many awards. I think it will take about 3 to 4 pages with the number of awards he has received, including S.B. Joshi Memorial Award and many others, of course. And he has received lifetime achievement awards from many organizations. So anyway, there's no point in discussing so many of them and not getting anything back in our minds. So with this little introduction, let me introduce our panelists today, who are very important for moderating the session in a way. Yes. So one of our panelists today is Mr. V.N. Hegde, a very nice and smiley person. You can see him probably on the screen. He is Chief Executive Officer of Stoop Consultants, and formerly he was Executive Director of Gammon, and Gammon is a senior professional with a rich experience of over 3.5 decades in construction sector in the areas of design management, technical management, site management, project management, and contract management of highways, bridges, energy structures like chimneys and cooling towers, and environmental, marine and hydraulic structures. He is a recipient of around 9 national recognitions in addition to an international prize various institutions, IRC, ICI, NDRF, IBC, and IABSE. He has more than 140 publications to his credit and is a member of various IRC and BIS committees who are responsible for preparing codes of various types. He is also a member of TG 10.1 of Federation International du Béton. That's a Swiss organization, or maybe French, I could be wrong, which is a special task group working on FIV Model Code 2020 now. Well, last one was 2010. Apart from being on technical board of ICI and academic board of SP CE, that is Sardar Patel College of Engineering. He is also a fellow of Indian National Academy for Engineers, INAE. So we have a very learned, highly profiled person with us who I'm sure will not let anything go wrong. But on the other hand, on the constructive side, he will reply to certain queries which may supplement the replies by speaker and by others. We have another panelist, Dr. Harsh Vardhan Subarao. He is another stalwart in the field of bridge engineering. Dr. Subarao holds a master's from University of Michigan and PhD from Imperial College London. He has been involved with a number of landmark projects such as Signature Cable Stayed Bridge, Delhi 4.6 kilometer rail-cum road bridge, Patna Bridge number 20 on JURL, metro viaducts, metros, viaducts, elevated roads, arch and extra doors bridges and underpasses. He is Vice President and a member of Technical Committee of International Association for Bridge and Structural Engineering, thus IEBSE Zurich, and Chair of his Bulletin Edit Board, member of Highway Research Board of India, serves on several committees of IRC, BIS, FIB, and various international and national bodies. He has over 35 years of experience and a number of papers and bridge projects to his credit. So we have a highly learned person amongst us, and he's of course the managing director of his company, Consumer Consultancy Private Limited. Friends, I think we all know that when we talk of cable supported bridges, we mean several types of cable supported bridges. There are suspension bridges, cable stayed bridges, extra doors bridges. But if you talk of India alone, India has constructed all these kinds, starting with a small one in suspension bridge technology, that's Akar Bridge in Sikkim. And of course, thereafter we had several bridges like Signature Bridge, where Dr. Harshvardhan Subarao and we as Tandon consultants were also involved in Delhi, where the pylon is on one side and it was designed by our speaker, Dr. Boris Reyher, who will be with us in a short while. We have bridges like Worli Bandra Ceiling, that's in Mumbai, which is a cable stayed bridge. We have Basoli Bridge with a 350-meter span in Jammu Kashmir. We cable stayed bridge, of course. We have Dwarka Bridge in Gujarat, which is under construction with a 500-meter span. We have Nivedita Bridge, which is extra doors bridge. That's another category of cable stayed bridges. We have Ara Chhapra Bridge, which is the world's longest extra doors bridge in Bihar. So India is not far behind. India is quite well catching up. So before my giving so many inputs to you, I'll request Professor Mahesh Tandon to address the gathering, address the audience. And sir, please, 20 minutes would be great.
Vinay sir, my suggestion, Vinay
yes.
sir, Dr. Boris has already joined. Just,
okay, then let me introduce Dr. Boris Reyher as well. Can I have the slide? Although I have the printout with me. Good afternoon, Dr. Boris Reyher. We have to wish good afternoon to you, considering your time difference. Boris Reyher, whatever I know, before I read out his formal CV, which he has sent in a very simple 6-7 lines, he's a very nice, cool, soft-spoken, and high-level technocrat. That's what I know about him. I have so far had only one physical encounter with him, and we were working on a project commonly together, that's SBP and TCPL together, and we gave him several problems that these are the issues that the client is facing before we bid for the project, and tell us what we can do. And he went back along with his colleague, Fernando, and they came back in the morning with all the mathematics, all the answers, all the sizing, and all the options. It was so very surprising that a person at his level, who's a director, can produce so much over the night. He doesn't need to sleep, I guess. So Dr. Boris Reyher has been working as a structural engineer with SBP since 2007, where he has directed the Berlin office since 2010. He was appointed to associate in appointed as associate in 2014 and was appointed as director in 2020. That's this year itself. Before that, he worked for Bureau Happold in England. After finishing his doctoral thesis in numerical mechanics at the Technische Universität Berlin, that's a German word, he studied civil engineering at TU Berlin and the University of Michigan at Ann Arbor. His focus is on bridge construction as well as steel, concrete, and membrane constructions for buildings, in particular research and application of lightweight concrete. That's what a lightweight tension roof of Jawaharlal Nehru Stadium, which was the Commonwealth Games 2010 venue in Delhi. So with these words, gathering, and nothing like managing a time well in about 20 minutes or so, sir. Please.
So I request all the panelists to, video mute themselves so we get a better bandwidth. Thank you. Yes, sir. Yes, sir. Over to you.
Okay. Good evening, friends. And I wish to thank IIBE for giving me an opportunity to share some thoughts on cable-supported bridges. And I'm very happy to see Mr. Devate, the Director General of IIBE, and of course, Mr. Vinay Gupta as the President of IIBE, and all the other people who are connected with the organization of this seminar. So let us start, since the time is short. There are really three types of the most popular forms of cable-supported bridges: suspension bridges, cable-stayed bridges, and extra-doors bridges. In view of the time limit, we will be talking about cable-stayed bridges essentially. The contents of my presentations are here, but let's not go through them. You can just see what they are. And as soon as the time runs out, I'm sure Vinay Gupta will remind me, and we will end there. So specifications and structural systems. There are at the moment these guidelines and codes which are used for the cable stay systems and cable stayed bridges. And extra doors bridges. Let me just tell you what they are. One is FIB Bulletin 89. This is essentially the year of the publication is written here. It is used mainly in Europe, but of course we use it everywhere else also, but produced in Europe. There is the PTI documentation, which is again on stay cable design, testing, and installation. Please note that this is all cable stay systems only. They are not talking about the bridge as a whole. But when you come to extra doors bridges, this IABSE bulletin, it covers really the whole thing, not only the stay cable design, but also the design of the bridge itself. There are the Japanese specifications published in 2012, which also are covering the entire design and construction of cable stayed bridges as well as extra doors bridges. In India, IRC is making two guidelines. One is B9.3, this is the name of the committee, extra doors bridges, and B9.4, which is cable stayed bridges. Apart from all these documents, Eurocode 3, part 111 also has some recommendations which we now and then refer to, because our codes are basically heavily dependent on the Eurocode provisions. Suspension bridges, just a word of that, the behavior you can see here, they've got a stake, they've got a cable which is going across like that, much like you know, a clothes where you have a rope and you you hang clothes on it. It's very similar to that. So this is always in tension, and on this tensioned cable, from there you have very closely spaced suspenders which suspend the deck on which the traffic moves. And because of these high tensions, you get a very heavy compression in the in this pylon or tower, as you can see that. Cable stayed bridges, the structural action is totally different, and let me just explain. The traffic, you know, is moving here, and you have steel cables which pick up the load, and they are always in tension. And because of this, both being in tension, there is a heavy compression in the pylon, which you see above, as well as on the pier below. If you see this particular junction, you have got tension which is coming like this. Supposing at the moment we are not considering some unequal loads. The whole bridge is loaded uniformly, and you can see that you can have very heavy tensions here, and this will give you a very heavy compression inside the pylon. As far as this particular junction is concerned, you have again a tension in the stay cable, and you have a compression to neutralize the horizontal component of this tension. So this heavy compression that you get is because of the tension that you have in the cable, and the cable is attached to the superstructure. So it is very simple to find out if you have uniform loads, how much is the compression inside this, how much is the tension. It is very easy to calculate, as is shown below in these equations. When you are talking about cable stayed bridges, this is what they normally look like, and we try to keep these anchorages somewhere here. If you have two planes of anchorages and cables, there can be one also in the center, which is in the median verge, but I think that we will not get into so much details. The stay cables, as far as they are concerned, routine checks of the individual components of stay cables are required, of course, including anchorages, the cables, the strands, etc. But representative samples of the entire stay system, including mechanical testing, which means fatigue and ultimate strength, and water tightness testing, to ensure the effectiveness of the protective barriers of the actual stay cable assembly, are also done. So individual components as well as the complete stay cable, this is what the codes and guidelines recommend that you should do. The design life of the stay cable is typically assumed to be 50 to 60 years, which means that it is much less than the bridge life, which may be taken as 100 years normally in all specifications. So this means that you will have to change the stay cable at least once, if not twice, during the lifetime of the bridge. Specifications require that stay cables can be replaced while the bridge is in operation with reduced live load. So although the live load can be reduced, but you will have to replace the entire cable. And the stay cable is actually, this is the entire cross section, as you can see. You have, each one of them is a 7-wire strand, which is first galvanized, and then it has a SDP sheathing or PE coating, which is extruded along with it. You have wax or grease inside. And this entire bunch of cables, which you can see here, they are encapsulated in a tube, which is the outer tube, we call it, or the pipe. Here you can see the anchorages, and each strand is got actually a separate wedging system, the anchorage system, so that you can de-wedge and replace strand by strand. You don't have to replace the entire stay cable at one time. And also, when you are inserting or installing these strands, it can be done strand by strand. It is not necessary to put all of them together. The stay cable actually requires some protection when you come close. This is the deck level. So at the lower levels, you require vandalism protection, also require fire protection. If you require dampers in stay cables, and many times we do, you can have an external damper, which is shown here, or you can have an internal damper, which is actually a neoprene washer, which you put inside, which is of some sizable width, so that it can dampen the vibrations. The anchors have to be very special, because as you can see, the anchorages have to hold on for the entire life of the cable stay, at least, if not the whole life of the structure. So it has to be very robust, and there are many tests which are required to be done here. They also have the fatigue testing, etc., which you can see here. The entire cable has been put in a tub, and at this end you have something which is moving and applying the something like 2 million cycles normally, and the upper level is can be 60% of the ultimate strength. This is what we normally test, but of course all the specifications have slight differences in as to what level and how many million cycles you have to do. Now, extra dose bridges and cable stayed bridges, they are slightly different, but they look alike. Cable stayed bridges, we have already talked about, as if you have an external load and the stay cables take it up to the pylon, and the pylon, of course, you get a compression. When you have a stay cable, the first thing you can notice is that the height of the pylon has reduced considerably. It's almost half the length, half the height of what it would be in the cable stayed system compared to the span. So in this, because there is a shallow angle here, it does not pick up as much vertical loads as we would like to, which means as would be possible in a cable stayed system. So apart from this, we also have to put a lot of pre-stressing cables to take the bending moment. So it's this extra dose bridge is actually somewhere in between a cable stayed bridge and a free cantilever bridge, which we all know about, and we have made many free cantilever bridges in the country. Of course, now there are a large number of extra dose bridges which are coming up, and I think there is a special publication which is also, apart from what is IRC is doing, there was also a special publication of ING IABSC which talked about the extra dose bridges which are coming up in the country. The live loads have, or the stress level change have a significant effect on how much proportion of the ultimate strength you can use in a stay cable. For example, if it is a extra dose bridge, you can go up to about 0.6 normally, and you will have about maybe 50 MPa would be the change in stress due to live load. When you come to a cable stayed bridge, there are the live load stresses are almost 3 times in the stay cables, and because of that, the fatigue requires that you go up to only about 0.4 or 0.45 times. So there is a big difference in the allowable stresses in cable stayed bridges and cables and extra dose bridges. This is the present world record. It is 1.1 kilometer long, the central span, and it is in Vladivostok in Russia. Here you can immediately see the difference. This is one of the earliest extra dose bridges which was made, and you can straight away see how short the pylon is and how narrow this angle is as compared to a cable stay bridge. The span range of this stay cable of the extra dose bridges is normally 100 to 200 meters, but of course, it's not something which is written in stone. You can go either way by a few or several meters. If you can just see these bending moment diagrams, when you have a cable stayed bridge, they are very closely spaced cables, as you can see here, and the bending moment that you are trying to achieve is very, very uniform. But if you see the extra dose bridges, which are shown here, you can see the bending moments are quite large as compared to what would happen in a cable stayed bridge. So the behavior is totally different in the two cases, and you require different kinds of specifications for the stay cables as well as the allowable stresses. Just one more diagram I wanted to show you. The low height of the extra dose bridge pylon results in a smaller angle with deck stays. This is the angle we are talking about. This angle becomes smaller, and the capacity to take vertical loads also becomes smaller because it's so the vertical component of the stay cable is much smaller. And of course, because of this shallow angle, you get a very large thrust or compression. So this is what is shown in this, the diagrams above. What would be the normal angles that you would get in a cable stayed bridge and in an extra dose cable? And what would be the force in the cables themselves? Multi-span cable stayed bridges are very important. This is a single span cable stayed bridge, and as you can see that if it does not cover the entire width of the waterway, then you may have to protect the pylons as they go down, and these even these piers are protected. Of course, if you have larger spans and multi-stay cables, all these problems get reduced. You have to protect them because of the barge impact or the ship impact, depending on what kind of navigation that is happening here. Multi-span bridges, India has very wide rivers. If you look at Ganga, Yamuna, at some places, you look at Brahmaputra, all these are very, very wide rivers. And if you are going in for cable stayed bridges, then you have to think of multi-span cable stayed bridges. This, of course, shows you a suspension bridge, but the principle is the same, that we have to have a number of load cases of live load that you have to consider when you are designing for a multi-span cable stayed or a multi-span suspension bridge. The problem with a multi-span bridge is that it becomes the stiffness is reduced quite a lot when the loads are unbalanced. If you have a uniformly distributed load right through, of course, the stiffness would be okay. But if I put loads only in, for example, in one span, you can see, because there is no stiffness here, and this has already made a rotation at this point, and you can see that it can deflect quite a lot. And almost always in cable stayed bridges, the governing criteria is the deflections. So if you can somehow reduce them, it will be much better. Now in multi-span cable bridges, how it has been done is that either you make the pylons very stiff, which means that you have a triangle in elevation. You can also have, for example, a support wherever you can put it, another support, so that it cannot deflect as easily as it would if there was no such support. You also have the possibility, this point does not move, it does not rotate. So if you put the top of the pylon and connect it here and here, this would be very much more stable as compared to what it would be without these backstays, or if you want to call it. There is also some idea of putting horizontal stay, just connecting the tops. There can also be an overlapping of stay cables which come from either side. So all these can be done when you are making a multiple span cable stayed bridge. And that is, I think, what we may require in India whenever we go in for multi-span cable stayed bridges. At the moment, we are doing a lot of multi-span extra dose bridges, but cable stayed bridges we have not done yet of this type. Here you can see one of the bridges in Greece, how they have made it is a multi-span cable stayed bridge, and how they have made the pylon so stiff. And here you can see the stay cables which are crossing each other from either side to make it stiff. At the moment, we have reached almost 1 kilometer as or 1.1 kilometer, the Rusky Island Bridge. And this was completed a 4 or 5 years ago. And you can see that there is a steady increase in the span range for cable stayed bridges. Let me go further. Design life, unlike a concrete normal bridge where we say the design life is 100 years, as far as suspension bridges and the cable stayed bridges and extra dose bridges are concerned, you cannot say the design life is the same for all the components. So it depends on which component you are talking about. Of course, if you are talking about the foundations and the pylons, etc., they would have a design life of 100 years, but not necessarily whatever is on the cables side. So each component of these type of cable supported bridges is different, and they are defined or they have to be defined in every design basis report so that you know what you are designing for. Some new concepts I want to talk about in the extra dose bridges. This is the
sorry for interruption, Professor Tandon. The presentation is very good, but another 2 minutes would be fine.
Fine. So
okay,
this cable stayed bridge, how it was done, can be seen here in this thing. That means that it was push launched. This technique is a different technique, and nothing to do with cable stayed bridges, but it was temporarily supported, and then it was push launched with, of course, temporary supports in the middle so that the span doesn't become too long. Here you can see an actual photograph of the thing being launched into position. Of course, these are temporary cables. They will be afterwards replaced by real cables. The other thing that has happened in recent times is the hybrid cable stayed and suspension bridge, which you can see here. Of course, Mr. Kasuga, who's actually very, he's really a genius as far as the extra dose bridges is concerned. He's calling it an extra dose and suspension bridge, but really it's the cable stayed and suspension bridge. And this has already been made in the 3rd Bosphorus bridge, as you can see here. And they have reached already 1.4 kilometers as the span. The Indian experience, I just want to show you a couple of slides, and this is how it is, just some photographs. Vidyasagar Setu over Hooghly Bridge, Calcutta, 457 is the mid-span, the span, and this was made by Schleich, Bergerman and partners, to which of which Mr. Boris Reyher is the director. We have Atal Setu over Ravi Bridge in JNK, 350-meter span. We have a signature bridge where again the same organization was connected, and that has a 250-meter span. But whenever you see this asterisk, it means that you have only a single pylon, and single pylon means that really speaking, this is 250 meters. So it is equivalent to almost a 500-meter span. Every time you see a single pylon, it means that you are really talking about a double the span as far as the design is concerned. This is the Naini Bridge over Yamuna, which is 260-meter span. This is the Kota Bridge over Chambal, which is Rajasthan, which is again 350-meter span. And there's another Atal Setu over Mandavi River in Goa, which is 150. It's a multi-span cable-stayed bridge. So this is all I want to talk about, that we have made quite a few progress as far as cable-stayed bridges are concerned in India. And this is the virtual handshake which I would like to do with you. And Jai Hind.
Thank you so much. That was really fantastic and a very good panorama of the cable supported bridges of various kinds and their technical comparisons we get. We want to know. Certainly, you have given it in a very right manner. And that forms a good preamble to Dr. Boris Reyher's presentation. So without wasting any time on any formalities, I would request Dr. Boris Reyher to please activate his presentation. And over to Dr. Boris Reyher. Good to see you after a very long time.
Well, thank you very much, Vinay Gupta, for the invitation to speak here tonight, this afternoon in my time. I'm very honored to be given the opportunity to speak to such a profound audience, and I'm actually very humbled when I look at the panel setup and at the qualifications and the experience of all the people that I'm seeing here. I'm also very happy and proud to see there's almost 200 participants in this webinar. It's a new format for me personally to speak to such a large invisible audience, but in these times it's probably the next best thing to really coming to India and speaking to all of you in person. I would also like to, of course, thank IABE for having me here and giving me room to speak and hopefully also discuss with all of you after the presentations. I'd also like to personally greet Professor Tandon, who I also had the pleasure to meet some time ago at his office. And yes, our offices have some common history together and work together. I also want to extend my greetings to the panelists, Dr. Subarao and Mr. Hegade, who will both reappear also in my presentation today. Vinay Gupta, you have said it before, India is not far behind when it comes to cable supported bridges. And Professor Tandon, you have just pointed out how many large and interesting cable supported bridges have been built in India in the recent years. I think this is absolutely true, and it's absolutely impressive. And when you look at the, say, the topographic challenges that India is facing with a number of very large rivers, and of course the mountains throughout, there is in the population and the growth and the need for improving infrastructure. I think India is looking at a very strong future also in the field of large bridges. for me personally, this is also very important and interesting because the company I work for, Schleichberger & Partner, has been involved in designing and helping to construct and build and maintain large cable-supported bridges in India in the past decades. And I have been lucky enough to be personally involved in a number of these projects. And I would be very keen, along with my colleagues, to continue these activities and to keep also these contacts alive that we have built up and that are working out tonight, for example. My presentation should be around 60 minutes. If I'm grossly over stressing the time, then you're welcome to interrupt me and stop me. But the title I have given in my presentation is Challenges in Cable-Supported Bridge Design. This, to be honest, is quite a very, well, general title, but let me make it a bit more specific what I want to talk about to you. There is, I would say, the term of challenges can also be read as an invitation to find solutions. And so I want to talk about 3 case studies today of cable-stayed bridges, or say cable-supported bridges, because in one case it's not really clear if it's cable-stayed or in other ways cable-supported. 3 case studies that my office has been involved in the design, in the conceptual design, in the detailed design, in site supervision, and in generally making sure that the structure can be built. And the sort of the red line or the thread that I want to take through the whole presentation is the question of how aesthetic and bridge engineering, so bridge structural aspects go together, can go together. They don't always go together. Sometimes you see a bridge where you say, wow, it looks really nice, but with an engineer's eyes, you would say maybe it's not the very efficient structure, or in other cases, sometimes you have a very pragmatic and efficient and cost-effective structure, but the aesthetics are a bit under the optimum. So I want to, one of my points will be try to show that just simply by reasonable and clean engineering and conscious engineering, you can actually automatically fulfill also some aesthetic expectations. And in the end, aesthetics is not just an add-on, it's of course also a function of a structure, because everything we build shapes the world around us. And we cannot just build things that are practical and cheap. We have to also consider, especially when we're talking about large structures, we also have to consider the effect that our work has on its surroundings and on the people that see it and that use it. So I want to give a few examples of, in my humble opinion, good engineering concept and good detailing will lead to an overall convincing solution. And you see 3 bridge structures here. The first one at the top, Yamuna Bridge Wazirabad, we have also already seen in Professor Tandon's presentation. I'm sure many of you as bridge engineers in India will have somehow seen this structure. Some of you I know personally have been involved in the structure and in the making and in the whole process that took a considerable time from the first sketch to the actual traffic opening. So I'm only going to touch this slightly and then move on to other structures which may not be so well known in the context here, which is another cable-stayed road bridge in Belgium, which I have personally looked after in the design and the site supervision and the erection advice and so on. And then finally, coming down in the scale, also in the size of these bridges, to a third project which has been constructed 4 years ago in Stuttgart in southern Germany. It's a pedestrian bridge, so it's a different task, it's a different challenge, but I'd like to discuss and show how also in footbridges very similar principles and thoughts and concepts can lead to convincing and pleasant solutions. So let me start with the biggest of my 3 bridges today, the so-called signature bridge across the Yamuna River. The setting, I think, is clear. It's an important road link out of Delhi And the Yamuna River is, of course, a seasonal river where we're here seeing at the moment the low water level. It looks a bit odd maybe that most parts of the bridges and the bridge in this photo is actually going across dry land. So why build a bridge there? But actually when you have the high water flood level, then this whole area will be flooded and the bridge will really then find its function. Let me just quickly go into a bit of a history. This bridge has kept us busy for something like 15 years, from the first discussions with the client, Delhi Tourism and Transport Development Corporation, DTDC. And in this picture, you see basically the core team that has been involved in the design and in the realization of this bridge. And it's actually interesting that it's a multi-generation project. In the center, the man with the white shirt and the red tie is Professor Jörg Schleich, the founder of our office. And to his left is the late Dr. Subbarao, and the two have been involved also in earlier projects in India, working together, and they have basically joint ventured for this project to deliver the structural design. To the right of Jörg Schleich is Mike Schleich, his son, who is actively a director of our company, Schleich Bergermann Partner. So this is one of the generation links here. On the very right, you see Dr. Harsha Subbarao, who is our panelist here tonight, and he is sort of the other generation link. So it's a bridge that has been some time in the coming, and it has kept different generations of engineers busy. And then the other two gentlemen from the right is Mr. Bansal and Mr. Sorry, I forgot the name, from DTTDC. Joe Skurian, I'm sorry. So the history goes even further back than this photo from 2005. So this is the second Hooghly crossing, which Professor Gupta has already shown before. And this was at the time, this was our first project as Schleich Bergermann Partner. When I say ours, it's of course not me personally, this was before my times, but this was at the time a record-breaking design, almost 500-meter main span cable stay bridge with a composite deck. I think it was one of the first cable stay bridges with a composite deck in the world. You see that here's a construction photo, how the deck is constructed of a steel girder grillage, which is then which is then complemented with a concrete slab. In this case, it was in situ concrete slab, which of course has some downsides when it comes to the structural efficiency and the early structural performance in the green concrete age. One of the very distinctive properties of this bridge design, one of the boundary conditions, was that the bridge was supposed to be constructed by local workers in the 1980s India, with local technologies, and weldable steel was a bit of an issue in those days. So the whole bridge was designed with riveted connections, so that low-skilled or unskilled workers from the region could actually find work here and get supported by this project. Sometimes later in the early 1980s, early 1990s, our office was involved in this multi-span cable stay bridge in Hong Kong, the Ting Kau Bridge, linking Ting Kau Island as part of Hong Kong to mainland China. So it's a very important traffic artery and business artery between Hong Kong and mainland China. And in a sense, it's a continuation and development of the technology that was used from the second Hooghly crossing, this composite deck. And here you can see a construction time photo where precast slab panels, in this case now, are placed on the steel girder grillage to form a composite slab which has some benefits over the in situ concrete, which I just mentioned before. So much for the history before the Yamuna Bridge. Now, how did the project start? The client called for ideas in the design competition. And one of the boundary conditions was that it had to be a bridge with a certain aesthetic impression. It was I think formulated from the beginning. It was supposed to be a signature bridge, and one of the requirements was that it would have double the height of the Qutb Minar. So this is already quite a challenge in itself, and an interesting thought to begin with, because normally you start with a span and develop everything from there. You don't normally start with the tower height and develop the bridge structure from there. But anyway, on the right-hand side, you see the original design of the bridge. So you see it's a unsymmetric cable stayed bridge. It has only one pylon, and the pylon isn't straight and it isn't standing vertical. So those are unusual features. Normally, when you look at most of the bridge cable supported bridges, you would have vertical pylons, which makes a lot of sense. But you also see that the cables on the left-hand side, so the cable supporting the main span, is not the same number as the cables going back from the tower to a fixed point. So this is quite an unusual design in itself. This is the picture of the final design. You also see that the bridge is not only an interesting geometry, but it has also an interesting color. And in fact, this peacock feather tattoo was conceived by our project partner and good friend Ratan Batliboy, who to my great pleasure is also part of the audience tonight. Great to see you. And this is now part of the whole aesthetic concept, of course. And here, of course, you see also the bridge in its sort of full function when the water level is such that the whole stretch that the bridge crosses is flooded, to justify the length of the bridge structure.
Dr. Boris, can I just request you to be a little louder or closer to the mic piece? So some people have raised this.
Okay. Okay, I'll try. Yes, I'll put the microphone right in front of me.
Please.
So this is a bridge elevation. Again, you see here there's a main span of 250 meters, which is cable supported, and there are several shorter side spans of 36 meters, which are directly supported by piers. And in the design phase, of course, there were several important questions. For example, with this special geometry of the pylon, for example, how do you figure out the wind load? So extensive wind tunnel testing was performed. A lot of engineering hours, of course, went into the detailing of the structural geometry and the optimization of the structural action. And you see a bending moment diagram of the longitudinal deck girders, where of course you will be looking for an even distribution of moments and a good ratio of positive and negative bending moments in order to arrive at economic cross-section designs. Talking about cross-section, this is the typical deck section, where you see in the outer axis A and B, you have the cable supported axis, and there's a steel main girder, a longitudinal girder, which takes the longitudinal structural action of the deck. And in the transverse direction, you have a steel cross girder topped by a concrete deck, composite slab. And the way this was actually then constructed was that the steelwork is a partially welded, partially side bolted girder grillage. As a matter of fact, the steelwork was sourced from China, so it was fabricated and pre-assembled, as we can see in this picture here, in a large steelwork plant in China. And then big parts in the biggest transportable sizes were put on ships and shipped to the Indian coast. And at the Indian coast, this process faced the next great challenge, which is transporting the large, heavy, up to 350-ton steel parts from the Gujarat coast to Delhi by means of road transport. And of course, you can imagine that a number of bridges along the way were not up to the load level in terms of their capacity. So temporary crossings had to be done through the riverbeds, which of course was only possible in certain climatic conditions. And then finally, the first pieces arrived. Here we see one of the feet of the pylons where the first steelwork piece was placed on one of the largest pot bearings in the world, with a 350-ton capacity, 3,500 tons capacity. And yeah, then gradually the deck and the steelwork grew. You can see that here the steelwork part of the deck is placed on temporary supports. Later then the concrete deck was added. The concrete, in most parts of the bridge deck, the concrete was a, as I mentioned before, a precast construction, full depth precast panels of up to 350 millimeters thickness. And of course, the question is, how do you effectively and economically join these panels to form a monolithic slab in the end, and to make sure that the bond with a composite steelwork is working well. And because of the previous experience with the Tinkau Bridge, we knew from the beginning that this was well possible with these hooped overlaps of bars. And here you can see a picture of a part of the deck where in the front you see some of the panels already placed, but not yet cast, not yet stitched together. And in the upper part, you see a large part of the deck between the pylon feet where you have a lot of transversal tension. So it was decided to have a complete in situ deck in order to be able to react to the force density better with the reinforcement. Other challenging details involve, for example, the tie down point of the backstay cables. You have seen in the overview picture these bundles of 2.4 very large 127 strand stay cables. They holding back the pylon, and they will transfer a very large uplift force to the foundations. Won't have time to cover the foundations. Harsa Subbarao would be the person to talk to about the challenges in the foundation design in this bridge. But above ground, you can see that there's also some very special construction here with rocker bearings, which are then pre-stressed to a large well foundation. Another interesting detail, and this is something that will also appear in the next project that I'm talking about, is the way that the cables are attached to the deck. And there's of course a large number of different options to do this. The classic, one of the classic ways I would say that has a lot of sympathy that we have a lot of sympathy for in our office is this steelwork connection that is above the deck, because the connection and the anchorage will also always be well accessible and inspectable, and all stressing operations can work from above the deck, and there's no need for complicated scaffolding underneath. Here you see a photo from how a new cable is installed. And Professor Tandon has shown in his presentation how generally a multi-strand stay cable is composed out of a number of strands. So here you see the so-called master strand being threaded into HDPE sheathing pipe, and then the whole thing is lifted up to the tower anchorage, and then the first step is taken towards installing all the rest of the strands, which is happening here. So here you see the cables already hanging down from the pylon, and now successively all the remaining strands are introduced and then step by step pre-stressed to construct the cable. Here you see the anchorage block at the bottom where a strand is looking out, and this will be fixed here with wedges. And when everything is finished, the cable anchorage will look something like this. So with a large number of strands poking out. Yeah, and then finally, when everything goes right, after a certain while, the bridge will be completed, almost completed in this picture. So here parts of the pylon head are still missing, but the cables are all installed, and the temporary foundations for the installation of the deck are actually already inactive and are being removed. And then, of course, the party can start. So the big celebration to inaugurate and hand over the bridge to its actual purpose, to the traffic, was a nice festival with an impressive laser show and a lot of visitors. So I think that's a very a nice moment when everything is finished and all the troubles and all the hardships have been forgotten and the bridge is finally there. And it's beautiful and it's visible, and we will always love to come back to it. Now the next project is a bit smaller. It's also a cable-stayed bridge, as you can see, also road bridge. It's located in Belgium near the German border. And this was a project where our office has been approached by a Belgian contractor who was bidding for a PPP. And there was a reference design by another Belgian engineer, very respected, world-famous engineer Laurent, and he had proposed this reference scheme of also a cable-stayed bridge with a single cable plane. And we discussed this with the contractor, and we decided to make a special proposal with a reduced span. So our bridge has moved the pylons further to the shore of the canals, which it crosses, to have only 125-meter main span and a 60-meter back span, rather than almost 200-meter main span in the reference design. So this was also, of course, informing the cost and the constructability. And what you can see in this overview drawing here is an elevation and a plan view. And you can see immediately that we are talking about a skewed bridge geometry because we have a skewed crossing of the canal. So this became one of the main subjects in our design work, to really carry this skew through every detail of the bridge. So this was a very central conceptual aspect for us. You see that this bridge has an interesting cable arrangement, which is called the Harp Arrangement. That means that all the cable stays are parallel rather than fanned, as you see in many other bridges. And it has visually, of course, a lot of advantages. It's much more quiet, but it has some structural disadvantages also, especially if you cannot have any tie downs in the backspan. And then you have to come up with other ideas how to support the cable forces in the backspan. And in this case, we decided to have a very strong and a stiff concrete deck in the backspan. Talking about the skew again, the skew angle of the bridge of the crossing actually carried through into even the shape of the pylons and even the geometry of the cable anchorages in the mast. So here you can see a photo of the steelwork fabrication, where of course the steel workers had quite a challenge here to make sure that this complex geometry was well constructed within the required tolerances. And here's a detail of a cable anchorage with a 160 millimeter thick butt plate. So there was a lot of angles here to be ground and be connected. And but I mean, challenges are always an invitation to grow and to get creative. Yes, this is a photo from the installation of the towers. So the towers are these skewed cross sections, which consist of steelwork, and then receive a concrete filling at the outside to form a composite structure for stiffness and also for durability. And you can see that at the lower level already the first deck cable is getting installed in the lower tower segment. The steelwork contractor also came up with a lot of good and effective ideas how to join and how to splice this construction. And yeah, a lot of work after the structural design is finished. Of course, a lot of work also goes in the construction engineering, how to lift things, how to transport things, how to connect things. Talking about connections, one of the more interesting details of this bridge was also the connection between the composite masts and the stiff pre-stressed concrete sidespan deck. So here's a bending moment connection to give extra stiffness to the backspan in order to reduce the in order to boost the overall stiffness of the bridge, especially for the main deck. And you see here that this is quite an onerous design, but designed with a lot of care to make sure that all the forces are transferred, and then also that when it's finished from the outside, there's a certain simplicity to the aesthetics. The contractor also went to great length to make sure everything was constructible within the required tolerances. So, for example, using here 3D templates to be placed in the formwork for the vertical pre-stressing tendons to hold, to tie them, to pre-stress the mast against the deck beams. And here you see how the first segment of one of the towers is being lifted in and put on top of these cast-in pre-stressing tendons with a lot of precision, and also with some clever methods how to adjust and how to properly position the mast. The backspan deck, as I mentioned, is a rather heavy structure to counterweight the light main deck. It's a thick concrete slab with upstand longitudinal side beams, which are penetrated by the cable tubes. And here are some details of the anchorages of the longitudinal pre-stressing tendons of these concrete beams in the side span. You see that even here the skew is visible in the offset of the anchorages in the formwork. This is an underside view of these formwork of these anchorage positions, which are then getting stressed from the underside of the deck. So you see that quite a complex geometry is coming out of this skew idea, and this decision to really do the skew in all aspects. These are transverse tendon anchorages in the deck between the towers. And here again, you see that the complexity of the formwork and requires a lot of skill and care by the contractors, of course. Another interesting point in this bridge, another focus point of attention for the detailing, was the connection between the composite main deck, mainspan deck, and the solid concrete backspan deck by means of quite special cast-in pieces and connections welded to the end of the main steel girders. You see here that there are brackets for the shear force, and that there are welded reinforcement studs for the bending moments, and there are also transverse for the transverse shear forces. There are some shear keys. So a combination of a lot of structural actions here, and you see also that in the installation of the rebar and the splicing with the reinforcement of the sidespan deck, this has been quite a challenge in the construction. The main deck itself will remind you in principle of the picture shown you before from the signature bridge at Yamuna. It's also a steel deck grillage, which is supported by cables at 2 axes. In this case, we have longitudinal girders, which are fully welded box sections. The transverse girders are open steel sections, and the whole thing is topped by precast concrete panels, which are then stitched together with in situ concrete. And it will come as no surprise that, of course, also this steel girder grillage has the same 22-degree angle skew as the rest of the structure has. Here you see some pictures of the installation. So the steelwork grillage, like in Yamuna, was transported to site in transportable pieces. In this case, the pieces were a bit larger because they were smaller, and because we had the canal as means of transportation. So things were put on barges with self-propelled trailers, and then shifted and rotated into position, and then put on temporary trestles. So this is only the naked steelwork without the weight of the concrete and without any extra loads. So this can deal with some larger spans than in the final configuration. Some words about the precast panels and the quality of those. You see here also in this picture, these are the precast panels which have a 250 millimeter general thickness. They're also skewed, of course, to match with the steel girder geometry. And I must say this reminds me more of Swiss watchmaking than concrete works. So this was really very high precision concrete works that were really impressive, and everything fit to the millimeter. So this is with due care and attention to detail, things can look on a construction site So here you see again panels having already been placed on the steel girders, but not yet cast. And in the front you can see the end basically of the side span concrete deck, and then in situ pours will connect everything monolithically. As we're talking about a cable stayed bridge, we have the process where we are assembling on site the stay cables from individual strands. So the cable contractor has delivered to site and laid out on the deck his strands for measuring. So you need to know exactly the so-called unstressed length of the cables before installation. So you know exactly how much to stretch them to reach a certain force level. And as in the Yamuna bridge, as I've shown before, the first step is to install the master strand of a cable with a sheathing tube, and then subsequently install the individual strands one by one to finally complete the cable. And you can see from this drawing here that for the Yamuna bridge, we have used the same types of connections between the steelwork of the deck and the stay cables. So the external elevated steelwork connectors above the deck, which form a very efficient way to join the two parts, and to also make sure that the structure is well accessible and inspectable at all times without much need to work under the bridge itself. So here again, very good quality steelwork, a lot of preparation and care in the process up which comes up to installing the cables. This is a photo from the cable anchorages inside the masts within a confined space. So originally we were planning to stress with a large jack, so stress all the strands simultaneously with a large, too complex with a space requirement. So we ended up stressing these cables strand by strand with a small jack. Also from under the deck, in case of the side span deck, where we have a concrete construction where you need to introduce the large cable force in compression and not in tension as in the steel construction. And then gradually the bridge grew and grew, and the cables were installed, and there were several stressing cycles until it was finally finished. Just some words about some more details. As I mentioned before, details really help and really define the quality of a structure. And here in this bridge, the contractor went to great length to also think about very small things like how the underside of these cantilevering decks will look like, and how to make sure that it has a nice overall appearance. Also very clean underside. This will not be seen by too many people except staff using the canal maybe on their ships, but it's just nice to see that our ideas and the clean concepts that we had in the design phase were actually carried through. Also, the side span deck underside is quite clean. It's just a simple concrete slab, but very pleasant. So this is the finished bridge. It was completed in 2014. And as a matter of fact, the canal you see here will be actually widened at the position of the bridge, so that in the final stage, the towers will really be standing right at the waterfront. Now for the third part of my presentation, and again, another step down in terms of size, but not a step down in terms of challenge, I would say, and in terms of engineering creativity that is required and that can be applied. This is a small pedestrian bridge of about 50 meters span in the town of Stuttgart in southern Germany, which is, a matter of fact, the hometown of our company. So Schleich Bergermann Partner was founded in Stuttgart in 1980 by Jörg Schleich and Rudolf Bergermann. And Jörg Schleich was a professor at the Stuttgart University of the time. And those of you who are active in international engineering associations or have been working in Europe will probably be familiar with the town of Stuttgart, because it's as far as Germany goes, I would say it's engineering hotspot. And so this is where we originate, and this is where we had the chance to build this little pedestrian bridge as a part of a new housing development. And you see it's kind of an interesting shape. It looks like a cable stay bridge, but it has, again, a pylon which is not straight, which is strange. And let me tell you the genesis of this geometry. So rather than starting with the truss analogy that is actually the foundation for a cable stay bridge, because the triangle is the most efficient structural system that we know. This bridge actually conceptually originates from an arch bridge. So an arch bridge, of course, connects the two ends of the arch. But what happens if you cut the arch in two in the middle? Then, of course, the arch would fall over unless you hold it back, for example, with a horizontal cable to resist the compression force at the top. But then, of course, the question is, what do you do with this cable at the other end? I mean, you have to fix it to something. So it would be a good idea to rotate the whole thing until your backspan cable reaches a point on the ground where you can actually introduce the force into a foundation. So this is the underlying idea of this bridge. It's really simple, but I would say the result is rather surprising, and it has not been seen so often. Again, the setting here, this is a former airstrip in the town of Stuttgart, which has long been abandoned in terms of aviation, but now it's the site of a large housing development, and there's a artificial lake that runs along. It's called the Long Lake, and so this bridge is called the bridge across the Long Lake. So you see the red bar here in the picture. This is the location, and it will enable residents of this future residential area to not have to walk around, but actually cross the pond. These are some drawings from the early design phase, and you see that this kind of banana-shaped pylon, it looks a bit like pure architecture, but actually when you get into the structural details of it and you actually think about the form finding, it's a very rational geometry as it translates the transverse forces that the cables introduce into the pylon into kind of an arch thrust, into a compressive force in the arch, which is then resisted at the top by this backspan cable. And you see also on the plan view that the arch has a transverse spread, just like the pylon of the Yamuna Bridge. So there's a certain similarity here. And you are able to walk through under these two pylon legs, and the cables will surround you in space. So as I said, the geometry, the whole the main span is almost 50 meters, and then there's this back span, or this backstay anchorage, which is about another 20 meters away. Again, quickly, how does this work?
But the tension that would be coming into the cables would need to, the pylon's eccentricity would need to be balanced. The shape of the pylon need to be balanced, and we could get away with one plane of cable. The other point is also that the two wells, the two foundations, are joined by a very deep beam, and that central pendulum bearing relieves the moment that would otherwise go down to the foundation, and the foundations become undesignable. They would simply not be designable given the soil and given the problems of that location in the ground. So I think that deep beam serves to distribute and get the portal action going between the two well foundations. And I think that's a very, very important redundancy built into the system in addition to what you said.
Okay, thank you. I have two questions from a consultant from Mumbai, Mr. Sandeep Patiwar. First question for Dr. Boris here is, cable stay structure side span generally is stiffened in the form of back short spans. Is there any other option like stiff deck? Dr. Reyher, if you like to reply.
Yeah, I mean, as I mentioned, there are different configurations of cables for cable stay bridges. And I mean, the main goal normally for a cable stay bridge is to support the deck over the main span, because that's where your main obstacle will be located. And in many cases, the side spans will offer opportunities for tie downs, for example, or for other support structures, as we just discussed. So it's really down to the specific boundary conditions of your bridge site, how the cable arrangement in the side span will be optimally be. The classic case would be the so-called fan configuration for cables, where you bring all the cables more or less to one point at the top of the tower, and then you're kind of free what to do in the backspan. You can fan them back out to support the deck, or you can just keep them concentrated in a bundle of cables and bring them down to a foundation level. So that this is very much specific to the actual project and the boundary conditions you're facing there.
Okay, one interesting question from a friend consultant of mine, Mr. Anjanelu Chunchu from Hyderabad. His question is, anybody can reply, either Professor Tandon or Dr. Boris Reyher. What is the shear transfer mechanism between precast deck panels and cast in situ concrete topping? As I remember, in Signature Bridge, there is no cast in situ topping.
No. There's no cast in situ topping, but there is
stitch concrete.
Stitches.
Stitch concrete between the panels.
Right. Yeah. Yes.
And then there are the shear transfer works with shear studs welded to the top of the steel girders.
And the stitch concrete, stitch concrete runs through the lines of shear studs. The shear studs are in the stitch zones between panels. The stitch concrete is poured over the where the shear transfer happens.
That's right. That's right.
After the panels have been stitched, it works very much like an ordinary in situ composite structure, where you have a monolithic slab, and it's connected via shear studs to the steel beams. There's no difference.
That's right. Okay, there's another question from Sri Maruthi for Dr. Reyher. How is the cable force analysis made in the case of this skew cable stayed bridge, especially knowing that forces in the cable on each side of the tower are not the same because of skew? What software is used to model and analyze?
Well, in general, it's done very much the same way as for non-skew orthogonal bridges. Of course, there are some points you have to be careful, especially when you're considering the construction stages, and you know, because you're building stage by stage, so you have to tell also the contractor at what construction stage to apply what percentage of the final force and so on. And of course, the whole issue of geometric control and the issue of how to pre-camber the steel members in order to arrive at the desired geometry in the end is a bit more complex in terms of in the case of a skewed bridge. But there's not a fundamental difference. I mean, you just have to be a bit more careful and maybe do a bit more detailed analysis. And as for the software and the tools we're using, at Schleich Bergermann Partner, we're used to using the Sophistic software package, which is quite a powerful and very capable software, especially for bridge engineering. It has a lot of features such as really geometrically nonlinear analysis, which is of course very important when you're analyzing cables, because the correlation between geometry and equilibrium cannot be neglected. So that's our tool of choice, and I think this is widely used also by other bridge designers in the world.
Yes, of late I think we are hearing of Sophistic a lot. In fact, they made a presentation to our company also a few days back, and he said it's a powerful tool for nonlinear analysis. You should be correct, I'm sure. So let us see how one can make use of it. There's another question from Sir Ravindra Kumar Golia.
Can I add one point? Can I just add one point about this? I don't know. Sure. I saw Kiran Madhvi in the audience list. So this is a bridge which Spectrum are doing, and he's in charge of Spectrum Consultants, and we're the proof checking consultants for that. I mean, that bridge has gone through a number of changes, but it will be probably India's first multi-span cable-stayed bridge, 5 spans, and that is being built at Ambora near Nagpur. and is there are 5 towers. And if Kiran's in the audience, he might ask a question, and that could provide some clues. But that's a 5 span, multi-span cable stayed bridge that is happening, and it's progressing quite well. I just want to add that one point when we're talking about multi-span cable stayed bridges.
No, thank you.
Happening in India too for cable stayed bridges, not extra.
You're recognizing your
and there is
associates through this webinar
and strangely, they use Sophistic, and of course we use Midas. So we have to do the whole thing completely independent of each other.
That's right. That's
Anyway.
right. That's right.
Right.
There's a question, partly common, partly interesting. The common part of it is that how important are the wind loads for cable supported bridges in general? How important in general and for signature?
Hello.
Are we audible?
I think there is a
Vinay sir, you're...
Yeah, it is audible.
So Dr. Reyher or Professor Tandon, anybody would like to say?
No, how important wind loads in cable supported bridges?
Am I audible?
Now you are audible. Now you are audible.
Is asked is how important are the wind loads, number one, and second is were there any changes made to the basic shape or geometry of signature bridge from the point of view of wind loads?
The second part, of course, I'll leave to Harsha and Mr. Hegde to reply.
Harsha or Dr. Reyher, anybody?
Or Dr. Reyher, any one of them. But I think the wind loads are a major issue. The longer the span, the more is the problem of wind loads. For example, in extra dose bridges, it's rarely a problem. Although people are doing wind tunnel tests and all that for some reason or the other, but really they are not required. And when we do make the some wind load document next time, we are going to say when it is required and when it is not required. The wind tunnel test. So the question is that if you make what is today is to make something which is a very streamlined shape with definite sort of dimension. There is no bluff surface which is stopping the wind, but it is just smoothly flowing through. And other things which have come now with now what they are designing with this 3.5 kilometer long bridge, etc. 3.5 kilometer span bridges that they are talking about. The main thing is the deck, how to reduce the wind load, and what is called the flutter phenomena. Flutter phenomena means that, of course, when with wind, the deck has some displacements, but when the displacements and the wind, the wind pressures, when they start acting together or interacting with each other, that's when you get this flutter phenomena, and many bridges have had the problem. But I think that once you are able to get over that, and that happens really on long spans, and if you have not taken good care of how to shape the deck, a box girder, for example, at the two ends should be streamlined so that the wind forces go partly upward and partly below. And now that 3.5 kilometer bridge has found that what they did in the Stone Cutters Bridge in Hong Kong, that you have the up and down traffic separated, and you have two decks basically, and in between you have a gap, so that the wind forces are much more reduced, and this flutter phenomena is also reduced. Now they are talking about two gaps when they are talking about a 3.5 kilometer long bridge. Otherwise, the wind forces, especially the flutter phenomena, would be very difficult to tackle. But with this two gaps, because in the middle they are going to put a tramway or something like that, and on the outer side, there will be the up and down road traffic. So this way you can get these two gaps between the complete deck, and it is much easier to handle. So wind forces, of course, they are the most important things to do when you have a very long span bridge. But in extra dose bridges, for example, it's rarely a problem.
Yes, I remember he talked about this gap in long bridges, I think on Monday when he made a presentation. Dr. Reyher, would you like to say anything about change of the shape? Was it necessitated in this bridge on account of the wind forces?
Yeah, I would just quickly like to add to Professor Tandon's explanation that also, of course, in cable stay bridges, the wind effects on the cables themselves is often an issue because they are, of course, very slender. And the circular cross, sort of the aerodynamic properties. So in the design, in addition to what Professor Tandon has beautifully explained about the global structural behavior of the bridge under wind excitation and wind loading, the local effects in the cables, and that is especially with respect to vibrations of the cables, which then may lead, if it's excessive, it may lead to fatigue issues, is always a point of attention in the design. With respect to the pylon shape of the Yamuna Bridge, to my knowledge, the wind tunnel tests have not yielded any results that led to a redesign. I mean, of course, the shape of the pylon was an evolution from the first napkin sketch to the final shop geometry. But as far as I know, of course, because of its geometry, the pylon offers much more resistance to the wind than a normal pylon does. But that is also because of its size and its stiffness has not been a real issue in the structural design.
That's a massive size.
Yeah, thank you, Dr. Reyher. Yeah, there's one more question for you now.
Can I just add that the shape, the two pylons being apart, there's a gap there between those two pylons, but they join and fuse at the top in the form of a namaste, welcoming you to the east of Delhi. That's the shape of the pylon shape is also a namaste shape, welcoming you to the east of Delhi. Iconic. Right. And that itself, it is capable of high wind resistance. And we did two wind tunnel tests, a cross-section test for the deck. The deck, we did a cross-section analysis to get the wind parameters and the constants. And we also did a pylon-based, which I think Boris showed. He showed a photograph of a wind tunnel test of the pylon that was done. Yeah. So both these were done to prove that they were quite effective, and there was no need to give any special aerodynamic foil type shaping to the ends. The point really is, cables can vibrate, the deck can vibrate where the longitudinal and torsional modes couple, and that's very deleterious. And you can get at one extreme galloping, which is, which is the phenomena for wind, which started the whole wind phenomena with the galloping bridge, which failed. But coming to the cable itself, it vibrates on its own, and that can be damped. But the wind induces cable vibration, and even rainfall, rain-induced vibration of cable. So we have to deal with the cable vibration in a different manner, which is what Boris was also talking about.
I think, but basically, cable-stayed bridges are much more stable than suspension bridges as far as the wind is concerned.
Yes.
Because in a suspension bridge, the whole deck is supported only by vertical hangers. That's it. But here you are starting from the pylon and holding very close, fairly close spacings, the whole deck. And especially if you have two planes of stays,
correct,
it's automatically, I think by an order of difference is the stabilizing effect. What would happen in the case of a suspension bridge as compared to a cable-stayed bridge?
So, Boris, there is one other question for you from Sushant Goel. Does the type of cable, OSS and FLC, have any influence on the structural damping of the pedestrian bridge in general? It's a general question.
Can you? I didn't completely understand the different cable type. Can you say it again?
Does the type of cable type, which can be OSS or FLC, have any influence on structural damping of pedestrian bridge in general?
Well, probably yes, but normally most of your pedestrian bridges will be on a scale where parallel strand cables are not really the choice, because they are quite expensive, and they only make sense if you have to build a certain cable length which you cannot prefabricate and deliver and install on site in one piece. So these multi-strand cables really come into play when other cable types like OSS strand or fully locked coil cables get too heavy and too expensive to be installed. So for most pedestrian bridges, I would say there would be a difference in theory, but it's not really practically important, because I've hardly seen a footbridge that had parallel strand cables.
All right, thank you. Another question for you. Yes, it's about your pedestrian bridge that you discussed. For the pedestrian bridge, was the deck concrete poured in a single bore in order to control the final geometry, or did the cables need second stage stressing to control the geometry during construction?
There was no two-stage stressing. As I showed in the pictures, the sequence was that first only the steelwork was erected and connected by the cables to the mast, and then the cable stressing procedure was just by jacking down the cable at the deck at one end. So this was a very simple single step process, which of course required to really have the geometry of all the steel parts correct, and also have to have considered the weight of the concrete, which was added later in one pour, to have considered that correctly, because there was no means of adjusting. I mean, there were some what do you call it, cable locks in the cables, where you could individually restress a cable in case anything would have gone wrong, but those were not used. So yeah, this is quite a different way to control the cable force, and it requires a lot of control also about the temperature and the conditions on site at the time of stressing. So all the calculations, all the erection construction calculations the engineer has to do have to also take into account the temperature at which this is done. Otherwise, it would probably not lead to the right cable forces.
Okay, good, thank you. Somebody has raised a question for Mr. Hegde on some project, COSI, etc., which I think best would be that he can reply him directly from the question box, as opposed to my taking into the common forum. So this forum is for the two presentations we had. Mr. Alberto Mizail, asks, if you allow me, consult about some bibliography. With that, you can consider we can understand very well the cable behavior. Well, let me go further. This, I think, can be asked or replied separately if they like. What are the special, by Kiran Madhukar, what are the special challenges in hybrid bridges, as we are combining stiffened cable stayed system with suspension cable system? I think this must be a question to Professor Tandon, who explained such things, the hybrid kind of bridges. What can be the challenges? So, Professor, we would like to...
Yeah, you know, like I explained that it's the wind forces, for example, are the most serious things to tackle when you go for a long span. Now we are talking about spans which are, you know, nearing 1 kilometer or going beyond that. in those type of situations, cable stay may not be the right solution. It's already the suspension bridge range that you are getting into. But if you put stay cables, by their very concept of holding the deck at close spacings and then attaching it to the pylon, makes it much more resistant to wind as compared to if you had only a suspension bridge. So I would say that the suspension bridge, when you add the stay cables, it will automatically reduce your problems because of the very nature of a stay cable bridge, which is much more resistant to this type of phenomena, this type of excitation, which would happen in a suspension bridge. That those problems would get tremendously reduced the moment you have the stay cables. So I think one of the great advantages, I think, and this is not new, the stay cables have been done, these hybrid systems, even in one of the bridges in New York, when you really see that, and a fairly big span.
Bridge.
Sorry?
Brooklyn Bridge.
Brooklyn Bridge. I mean, if you really see that, it was a very substantial span. I think it was at least maybe half a kilometer or more. I mean, at that time, they made it into a suspension bridge, and with the stay cables. I think it was more like a kilometer, if I remember correctly, the Brooklyn Bridge. So it's an old concept to do a combination of this hybrid system. And to my mind, the biggest advantage is the reduction of the wind effects.
Thank you. Can I answer?
Yes, Mr. Hegde, please.
Yeah. You see, the days what used to happen was the analysis used to be very difficult to combine the system of, like the stiffness and kind of thing and all. Nowadays, the analysis, because of the advent of computers, has become much simpler than earlier days. With the advent of computers, analysis is becoming simpler. It is possible to, combine the stiffness, the different kind of stiffnesses together now. In my opinion, I made this presentation in 2000, I think perhaps in 10, in the Delhi FIB International Conference, where to increase the spanability, it will be the combination of all kinds of bridges. It will start with the cantilever bridge. The cantilever bridge, the same pylon will be having all kinds of cables. In the sense, the same pylon, it's possible for us to have the extradose cables, then the stay cables, then ultimately at the top of that a suspension cable. That suspension cable will be only holding this by the vertical, by the virtue of that vertical suspenders at the mid span, some span. That because while designing the suspension system, I explained earlier the deck system design as well as the cable system design is independent of each other. It's not connected to each other. So to increase the spanability, I think it will be the hybrid combination of extradose, cable stay, as well as the suspension bridge is the way forward. If at all, if you want to increase the span of the bridge. But because the analysis has become simple these days.
Okay, thank you, Mr. Hegde. There's another question, I guess, for Dr. Boris Reyher. Is from Mr. Vipul Prakash. The question is, how much adjustment can be made in the length of a stay cable while it is being jacked and afterwards during its service life?
I didn't get the first part of the question.
How much adjustment can be made in the length of a cable stay or stay cable while it is being jacked, that means during construction, and afterwards during its service life?
Okay.
Can the cable be stressed?
Yeah. Okay. Yeah, that's the biggest advantage, I think, in this type of cables with the parallel strands. that they can be restressed, they can be replaced, or they can also be restressed or even unstressed. So the stress can be increased or lowered in a single strand at any stage. I would say the limit to the amount you can stress it is of course given by the fracture strength, which is quite high, which is on the order of 1800 MPa. But there's much more importantly, there's a limit to how little you can restress or de-stress a cable, because if you remember, I showed this picture of how the strands are locked into the anchorage body by means of these wedges, and these wedges are basically just little steel parts that have teeth on the inside, and they cut into the steel of the wires, and they actually hurt the wires that way. And so if you restressing a cable, you have to make sure that you restress at least the length of a wedge, so you don't overlap these bites. So so I would say the actual maximum amount you can stress a cable is just defined by the elastic modulus and the strength of the cable. But it's typically, I would say, for, well, also depends on the length of the cable, but it could be on the order of well, several decimeters that when you install a cable from its unstressed length to the final configuration, that could be several decimeters of stressing length typically, but it depends on the size, on the length of the cable, and of course the strength of the strand.
Thank you, Boris. We
Vinay,
have at least...
Vinay, I have a question to add, because the last bridge, which, something fantastic he showed about the first use of carbon fiber cables.
Fiber cables, yes.
I would like a little more discussion on that, because that is pure innovation, taking away fatigue from what is a fatigue-prone bridge. Okay. And, that's the failure of the network. The downfall of the network arch bridge, or the downside, if you like, is that fatigue issue. Now, a network arch, typically we cross two planes. The network is done by crossing two planes of cable and giving it that rigidity. Now, I'd like to ask Boris about what this new innovation, what all testing had been done, or what's the kind of, what's the carbon fiber, the strand, and a little bit more about how it's anchored and things like that.
Okay. So we were in the middle of the design of this bridge when we realized that with normal high-strength steel hangers, we would not be able to overcome the fatigue issues. And then we started to research the market for commercial carbon fiber composite tendons that could be used in the structure. And we actually found a Swiss company that makes these tendons and also the anchorages. So in principle, they work pretty much like a stress bar, like a McAlloy bar, for example, in steel construction, where you have a flat fork connector at the end. And of course, we had to do substantial testing, but that was more not down to the fact that the product wasn't properly developed and tested in itself, but of course the German building regulations do not cover carbon fiber components, and especially not the ones for light rail bridges. So we had to convince the authorities and the traffic company that we would meet actually all the strength and fatigue and durability requirements. So we had to do a lot of special testings for load cycles and ultimate strength. But they were so convincingly successful that we could basically answer all those questions and got the approval in the end. But this is, of course, the problem with all novel construction that, or all innovations in general, that you have to basically overcome the skepticism and the and the conservatism in many places. But yeah, it was successful in the end, and actually now we have, because of this bridge, we have been approached in a second instant by German railways for a 100-meter span bridge crossing the river between Germany and Poland, to come up with a alternative design proposal, because the original network arch that their designer had come up with got stuck at exactly the same point in the design with the fatigue issues.
Thank you. Very interesting. Thanks.
We have also attendees from UK, and one Andrea Francini from University College of London has asked a question: which kind of structural optimization approaches are you applying or have you applied in the design of cable-stayed bridges, and which developments do you do or do you expect to do in future, for future?
Well, structural optimization is a widely used term, and the question is, what do you actually mean when you say that? I think when it comes to cable-stayed bridges, the optimization is more making sure that the bridge will be in equilibrium, and you are designing the geometry such that you are really finding the equilibrium of all vertical and horizontal forces without any bending effects. I think that's the most most important key to cable-stay bridge design and shape finding. I wouldn't exactly call it optimization, because once you have achieved this pure tension and compression geometry, then it's you don't need to do a lot more in terms of shaping or in terms of defining the geometry of members, because everything will be either in compression or in tension, and that's the most efficient structural action. When we look at this pedestrian bridge I showed, I was actually talking about form finding, and because this structure only really works in compression and tension if you have the catenary geometry basically of this arch line, and it's not obvious, it cannot be derived without form finding mechanisms. We actually have some experts for that in our office. As you may know, we're also active in the field of lightweight structures, so spatial cable and membrane structures, and there of course also form finding plays a great role in defining efficient spatial structures. And we use the help of these guys to basically define the catenary line of this half arch.
Right. Thank you, Boris. There's a question for Professor Tandon. To avoid, this is by Dr. J. Prakash Arul Jose. To avoid corrosion in cables, what precautions measures are we following, sir?
You see, the concept now is that one protection measure is not enough. You have to have multiple levels of corrosion protection, which have to be provided. For example, the bare strand, you can do an epoxy coated strand, or you can galvanize it, and that will be one level. Then you have you have got a PE duct or PE tube in which it is extruded. That will be another, and the grease will be there inside. So you have another couple of levels of protection here, because now between the big tube or the big pipe, which encases all these strands and the strands themselves, there is nothing. In the old days, we used to put grout, and in one case, for example, even in the second Hooghly Bridge, they have put some polyurethane there inside, which is a pretty costly proposition. And now if you can somehow reduce this there's so many operations, and to start with itself, you start with 3 or 4 levels of protection. Then I think that is what you can do as far as corrosion is concerned. And that is another reason why you cannot say that the corrosion protection is going to last for 100 years or something like that, because the primary protection which a concrete provides to a normal cable in a normal bridge, that is not available when you have something which is external. So you have to find other means to replace this concrete, the protection that is provided by concrete. And that is why you have so many other things to do. Like you can have an epoxy coating, you can have galvanizing, you can have HDPE extruded kind of a strand. So all those protection, and of course the pipe itself, it has to be made absolutely watertight. There are tests even for that. Like I mentioned, that apart from the fatigue, you also have to have a water tightness test, because you cannot afford any water to come there. Even after doing all these levels of protection, you still have to have something which is completely watertight. So that is what we do, multiple levels of protection against corrosion. That's the only solution. And to keep whatever is in the pipe, all these strands, they must be completely excluded from communication with the outside atmosphere.
Thank you for the comprehensive reply. I think let's go to the next question, which is from Sony JSD. What about cost and durability of carbon fiber hangers compared to steel hangers? I think it's very easy to say that here we use steel, here we use carbon fiber. This person asks, how do you decide between the two? What is the comparison of the cost, the lastivity, the life, and anything else? So, Dr. Reyher, would you like to?
Yeah, this is a very, very important question, of course. I think at the beginning of the introduction of new technologies and new materials in the construction industry, there's always this problem that you have very little competition when it comes to sourcing new materials or new products. So some companies have pioneered, of course, years ago in producing carbon fibers for industrial applications, and in some other industries, be it the automotive or aerospace, carbon fiber products are much more widely used by now because of their specific benefits in terms of weight and strength. Or if you buy a mountain bike, for example, a carbon fiber frame will still be a little bit more expensive than a good aluminum frame, but not on the order of magnitudes. In the construction business, it's still quite different. If you want to go out and buy a steel hanger, like a steel tendon, a stress bar, it's not very expensive. If you want to buy the same product in carbon fiber, you first have the problem to find somebody who can sell it to you, and then the next problem will be that there's basically hardly any competition so far, so it will be a lot more expensive. I cannot tell you the numbers right now out of my top of my head, but there is a price you have to pay for innovation. Literally, it's not just the effort and the perseverance and the overcoming of all the troubles that you didn't think about when you started it. It's also literally a price in terms of investment. But I think what we could convince the client of in the specific bridge project was that the durability and the lack of need for maintenance and replacement of these hangers, as it is expected over a long service period, really convinced them that this, even if it's more expensive, say even by a factor of 2 or 3, just for the hangers, I mean, this has to be seen in relation with the cost of the whole construction, of course, because the steelwork will be the same price, the foundation will be the same price, the erection process will be more or less the same. So this will you know, it will stand in a certain relationship to the overall cost, and then it's maybe not so grave anymore. The connection technology is pretty much the same as at least on the steelwork side. It's a luck plate with a drilling, and the rest comes from the carbon fiber tendon system. So it's not very much different. Yeah, so I think it's a matter of time until this technology specifically has established itself somehow in the market. And of course, we may be the first who have applied it to a network bridge. We will hopefully not be the last who are doing this. We will be very happy if other designers are also doing this kind of thing, so that there will be some kind of you know, movement in the construction industry. Because the first question you always get asked as a designer, if you propose something innovative, you get asked, you know, has this been done before? You know, where has this been proven? And then you have trouble explaining why it should work if it's never been done before. You know, so the more we do this, the more innovation we actually pushing forward as designers, as contractors, the more we will see in terms of progress.
Thank you, Boris. Bidan Devnath is thanking both the speakers for the fantastic presentations you people made. At the same time, he is also very happy to see Mr. V.N. Hegde after 7 years, and he's congratulating him. So something good to connect, you know.
Thank you.
Now we have a question from our one very well-known person, Dr. Lakshmi Parmeswaran from CRRI or CSIR. What is the live load considered for design of cable-stayed bridge? How do you decide the boundary conditions depending on whether it is wind or seismic action which is governing in the design? And she requesting Dr. Boris Reyher to kindly reply.
Well, the live load models are clearly documented in the Indian standards, I would say. So there's some not much choice you have. And the combinations, if I understand the question right, the combination with other types of loads is also part of the safety concepts that is fundamental to the code of practice system. And I think in the Indian system of IRC and IS codes, there is quite a bit of movement at the moment. Some new aspects like LRFD, load resistance factor design, has been introduced as a replacement for a permissible stress design. And certainly the load models are getting updated to reflect the actual traffic situation and axle loads. Yeah, that's all. That's basically defined by the clients and by the country and by the situation where you are.
Okay, thank you so much. I think it's been a long haul of questions, and so many questions could be taken because Dr. Boris Reyher took less time for his presentation. Otherwise, we would have been tired as it is and would not have taken any further questions. But there is one last question, I think, let me ask Dr. Boris Reyher, which Mr. Ajay Tank has asked for skew bridge. Is any particular reason to follow harp arrangements of cables and not fan type arrangement? Is fan type arrangement always economical or not?
Yeah, I mean, this was more or less a aesthetical decision. If you imagine you have two sets of cable fans where every cable has a different angle to the horizontal line, and then you basically overlay the two, because in a skew bridge there will never be any perspectives where these two fan arrangements will sort of match visually. So it will be a very, I would say, not a very calm picture. Of course, perspectives are always theory, so you will never see the bridge as you are drawing it in a parallel projection. But we specifically applied the principle of a harp configuration in order to avoid this interference of the different angles, and in order to avoid a messy overall impression of the bridge. You can say it's just an architectural decision, but I mean, as I tried to explain before, the visual qualities of a structural design will also be a central argument in the question whether it's going to be accepted and it's going to be welcomed, or it's going to be sort of rejected by the people who are seeing this large structure and who are using it. So I think it's apart from the efficiency and the economy of the design, this is also an important factor.
Thank you, Dr. Boris Reyher. Thank you, Professor Tandon. I think we had one of the best sessions ever today. And I'm sure everybody must be also satisfied with the replies, and all the panelists also made their complete contributions to best of their ability, I'm certain. I see we have in IIBE, I must say, we have one honorary secretary, that is Mr. Swapnil Joshi, who did the welcome to all of us. And we have one more honorary, of course, Swapnil Joshi, his company, that is Tento, they work in project management techniques, computerized techniques, and mobile apps also are prepared for that and things like that. Deepika Singh is also with him. On this side, Ruhi Agrawal, and we have Dr. Gopal Rai. Dr. Gopal Rai is the director and CEO of his company DGC, Dhirendra Group of Companies, and they're like doctors. Once the bridge is sick or a structure is sick, they come in and retrofit using whether it's fiber wraps or it's a pre-stress fiber case, or it is pre-stressing, or it is jacketing and all that. So Dr. Gopal Rai has been a very active honorary secretary of this organization for a very long time. I will request him to kindly propose a word of thanks. Dr. Gopal Rai.
Thank you very much, sir. Hope I'm audible.
Yes, you're fully audible.
Yeah. First of all, I will not ask one question to Dr. Boris, whether you listen to guitar or you play guitar also.
I do both.
Very good.
Whether you listen to guitar or you play also. I can see one of your hobby as whether you play or you listen also.
He said he does both.
I do it both.
Okay, that's I think that we have invented apart from a bridge part, because when I gone through his profile, okay, I found that he's fond of playing guitar or listening to the guitar. So I got the
cable supported bridges.
Yeah. I think the inspiration came from the guitar only. I think there also cables are there. Somewhere the cable connect him. Thank you very much, sir. Thanks to Vinay Gupta ji. Thank you very much. Let me do a formal conclusion. I think today our like the pioneer who has opened this IIB, Engineer MC Bide, he was very happy. Let me give the statistics of today. Today almost plus or minus 8 hours country, plus or minus 8 hours country have seen this webinar. Means plus 8 hours, minus 8 hours. And close to 570 people have seen today's webinar. So I think we should give a big applause to both the speakers. It's a benchmark we have set in IIB. This is another benchmark we have crossed. Let me thanks to Professor Tandon, always authority in bridge. We always, when we say bridge, the synonyms is Professor Tandon. Okay, so it's like that. And really thanks for accepting for today's talk in a very like in a short while we discussed yesterday, and we have discussed a long thing on the COVID achievements and all what we have done. Professor, for although unfortunately I could not able to attend, but yes, I have attended in last 10 years a lot of your lectures. Thank you very much, and thanks for accepting the invitation to speak on today's talk. Really, thank you very much. Then next, thanks to our today's like speaker, Dr. Boris. I think thank you very much for accepting. Although the are very keen to listen towards the subjects, and you have a best expertise around you. And thanks for again keep joining the talks on the IAB, please. And this is only the association actually in the Asia, or I can say precise, who's focusing on the bridges. And I think you are discussing on the carbon fiber, and the carbon word fiber is close to heart. Okay, so in 2007, when I started my career in rehabilitation, the cost of carbon fiber in rehabilitation was 10,000 rupees per square meter, means close to Indian rupees. Now it is 30% of that cost. So we have eliminated too many people who are just trading the more or less equivalent conventional way. So come in bridges also, the carbon will be the most things. Okay, static reasons. Then let me thanks to today's panelist, Engineer VN Hegde ji. Thank you very much, sir, for your valuable suggestions and valuable guidance. You are the mentor all around for the presentation which has been given, and thank you very much. Then next, thanks to our own Dr. Harshvardhan Subbarao, sir. Thank you very much for guiding us. In fact, like you have such a vast experience on the national and international forum. Thanks for guiding whole the team. Let me thanks to architect Ratan Batlimoy. Thank you very much. We just came to know the architect from this, and we have seen you. Thanks for joining us. Then let me thanks to R.K. Goyal from Indian Railway for his valuable suggestion, and like railway is trying to go for a cable stay bridges. Thank you very much. That thought can go ahead. Then let me thanks to Mr. Jatkar for his valuable suggestion. Then one of the very new invitee, Mr. BP Khare from Bhopal, from Madhya Pradesh. He has also joined today. Thank you very much, sir, for this. Now our own moderator and president of IAB, Engineer Vinay Gupta ji, बहुत धन्यवाद. And keep inviting good speakers. Like today we have reached a milestone. Now you have to break another milestone. Okay, keep inviting so that IAB can spread out. Let me thanks to our Director General, Engineer Divte. Thanks for his valuable time and talk. Now my own colleague, Engineer Swapnil Joshi. If somebody is doing very hard work in this COVID situation, is Engineer Swapnil Joshi. He has made an app by which you can control your project sitting on the mobile or the computer with the single dashboard. So I think the things are getting inverted. Thanks to Intento. Thanks, Swapnil, for making such solutions so that construction industry can survive. Thank you very much. Thanks to Deepika Singh, the colleague of Swapnil Joshi. Thanks to Ruhi Agrawal. From last 10 days, all pain has been taken by her, and she's keep on doing. Thank you, Ruhi. And more than this, you can become a member of IAB. The best part, by becoming a member of IAB, you can
looking at me like that.
1,700 technical paper, which is on our website, 2,700. Okay, 27,000, sorry. The technical papers are kept on the website, and you can refer to that. Thanks to Mr. Josefa, who is our like all Zoom and all arrangement on Daksh solution he provide. With the last line, I will say, with the permission of moderator and all the dignitaries, always look for ways to build a bridge instead of putting a wall. So with this note, I conclude vote of thanks. Jai Hind.
Jai Hind. Thank you so much.
Thank you very much.
And my hearty thanks to Dr. Boris Reyher for having spent so much of his time and energy on this little presentation for us. Thank you so much. Thank you, everybody. Good night. Stay safe. Stay happy.
Thank you, everyone. Thank you very much.
Good night, everybody. Thank you.
Thank you.
Boris, I didn't know. Boris, I didn't know you were from U of M as well.
Thank you, everybody. Bye.
Thank you, sir.
Yeah. Okay.
Okay. Thank you.
Thanks. Wonderful session. Thanks.
Thank you, everybody. Thank you, Mr. Goyal.
Thank you. Thank you very much.
Ruhi, you can close the session.
Okay.